Hey, welcome back guys. So I'm back with another video on advanced modeling concepts. So today the topic is support vector machines. We will see what support vector machine is, then what is the cost function for support vector machine, then bias variance trade-off in support vector machines, and then a quick comparison of SVM with logistic regression. And in the end, we will do one assignment on it as usual. Alright, without further ado, let's get started with our first topic, support vector machines. Support vector machine is a supervised classification technique similar to logistic regression. SVM uses a hyperplane as a decision boundary to classify the data points. Now hyperplane is nothing but a subspace whose dimension is equal to n-1, where n is the dimension of the space. So if we have two variables, then hyperplane shall have one dimension. If we have three variables, then hyperplane shall have two dimensions, and so on. So let's say we have these apples and oranges and want to classify them using support vector machine. Now let's say we have this hyperplane that classifies the data. What we will do is that we will measure the distance of each point from this hyperplane. Now the minimum distance between a point and the hyperplane is called as margin, which is shown here on the screen. Then we will select another hyperplane and we will measure the distance again from each point. Then another hyperplane, and same thing, we will measure the distance again from each point, and so on. Now let's suppose the distance between the first hyperplane and the closest points were 3 and 4 as shown here, which is the margin for this hyperplane. And the distance between second hyperplane and the closest point are 2 and 4 as shown here. And this is the margin for this hyperplane. And the distance between third hyperplane and the closest points are 2 and 1 as can be seen here. And this is the margin for hyperplane 3. So we select the hyperplane that has the largest minimum distance or largest margin. So what did I say? As we saw in our case that the hyperplane 2 had minimum distance as 2 and 4, and for the hyperplane 3 it was 2 and 1. So clearly the largest minimum distance is for the first hyperplane, that is 3 and 4. Hence we will select this as the decision boundary. Now observations lying exactly on the margin are called support vectors. But wait, in an ideal world, whatever we had discussed so far would have surely worked, and then nobody would have cared about us and it was all just simple. But most often we come across cases where there is no completely separable hyperplane that exists. So what do? We bring another concept which is called soft margin. Now what is soft margin? We use soft margins to allow few observations to deliberately misclassify. Here we use slack variables denoted by the letter psi. Slack variables in any optimization techniques are introduced to relax the stiff constraints. Like in our case, we are relaxing our constraint of misclassification and allowing few data points to misclassify deliberately. Now in this case, the value of psi lies between 0 to 1 if the misclassified observation lies within the margin, and it is greater than 1 if it falls beyond the margins. Now soft margins or generalization of maximum margin classifier to non-separable case is called support vector classifier. Now if we extend the support vector classifier and generalize it for nonlinear cases, this will become support vector machines. In this case, the decision boundary is complex nonlinear function. So what did we learn so far? We had multiple hyperplanes and we selected the hyperplane based on maximum margin classifier. Now what is a maximum margin classifier? It is the largest distance between the hyperplane and the nearest point. Then the points that lie exactly on the maximum margin classifier are called support vectors. However, very often we come across cases where a clearly separable hyperplane does not exist. So we deliberately allow few points to misclassify. This is called support vector classifier. And then when we extend support vector classifier to nonlinear decision boundary and generalize it, that is called support vector machine. So I hope this sort of clarifies everything now. Now how does SVM do what it is supposed to do? Well, it uses something called kernels. Kernel is a complex function that systematically finds support vector classifier in a higher dimension. So what does this mean? Well, it's a function that takes low dimensional input space and transforms it to a higher dimension space. Simply put, it does some extremely complex data transformations, then finds out the process to convert non-separable problem into a separable one. So that's what it does in a nutshell. Now we don't have to go into the nitty-gritty of it, how it does it, etc. We just have to know what is the purpose of kernels. Everything will be done by the software for us. So we also have various types of kernels and we have to choose the suitable kernel for our need. First we have linear kernel. These are the simplest and the fastest one. We use it when n, that is the number of features, is large and m, that is the number of observation, is small. Then we have Gaussian kernels. We use it when n, that is the number of features, is small and m, which is the number of observation, is large. Kindly note, it is recommended to perform feature scaling before using Gaussian kernel. It requires user to choose a value of smoothing parameter which depends upon bias variance trade-off. We will see bias variance trade-off in the upcoming slide. Third type of kernel is polynomial kernels. Polynomial kernels almost always perform worse than Gaussian kernels. Here we have to define two constants. First is degree of polynomial and second is intercept. There are many more kernels and we will not go into the details of it. These three are enough for us to know right now. Now, like any other technique, there has to be a cost function for this technique as well. The cost function for support vector machine is a hinge loss function as shown here. It looks a bit scary, so you don't have to remember this. I'll just explain what this function is saying. It is simply saying that when the point is within the margin or incorrectly classified, then the loss is simply 1 minus yfx, where fx is a linear function, and if it is correctly classified, then it is 0. Now the next question is, how do we do bias variance trade-off? We have a regularization parameter called lambda. The regularization parameter lambda serves as a degree of importance that is given to misclassifications. So as lambda grows larger, the lesser the wrongly classified examples are allowed, or high is the price we pay in the loss function. In short, as we increase lambda to infinity, our margin becomes hard, and hence no misclassification is allowed. Thus, it will lead to overfitting, and it will have low bias but high variance. On the other hand, if we decrease the lambda and it tends to 0, then it will have soft margin, but it will lead to underfitting, which in turn will lead to high bias and low variance. We also have to do a bias variance trade-off when we use a Gaussian kernel parameter. It is given by the below equation, and sigma here controls the bias variance trade-off as shown here. So as sigma square increases, it leads to overfitting, hence it will lead to low bias and high variance. And as sigma square decreases, it leads to underfitting, hence it leads to high bias and low variance. So that is the trade-off we do. Finally, let's see a quick comparison of support vector machine with logistic regression. Here if n is large relative to m, for example n is equal to 10,000 and m is equal to 10 to 1000, then we use logistic regression or support vector machine without a kernel, that is linear kernel. Now if n is small and m is intermediate, for example n is equal to 1 to 1000 and m is equal to 10 to 10,000, then use support vector machine with the Gaussian kernel. And if n is small and m is large, for example n is equal to 1 to 10,000 and m is equal to 50,000 plus, then support vector machine with Gaussian kernel is usually very slow. And one recommendation is to create new features and then use either logistic regression or support vector machine with no kernel. So it totally depends on the problem at hand, and accordingly we select the algorithm. So alright guys, that was all from support vector machine. I know it was a bit tricky one, but we finally did it. Now let's quickly revise what we have learned so far. In support vector machine, we understood what support vector machine is, then what is a hyperplane, then what is maximum margin classifier, then what are support vectors, then what is a support vector classifier, and finally what is support vector machine. Then we also saw kernels, the cost function, the bias variance trade-off, and a quick comparison of logistic regression with support vector machine. Now in the end, we'll do an assignment on it in R. So let's get straight into it.